Hey everyone, welcome back to the channel. Raise your hand if opening your electricity bill feels like a mini heart attack lately. Yeah, we've all been there. And maybe you've started dreaming about energy independence. Generating your own clean power and having backup when the grid lets you down. Well, if that sounds like you, you're definitely in the right spot today. We're diving headfirst into a super exciting project, installing an 8 kilowatt hybrid solar power system. This isn't just about slapping some panels on the roof to save a few bucks, it's about taking control over your power, control over those bills, and crucially, having peace of mind knowing you'll have backup power when the lights go out in the neighborhood. Now, before we get our hands dirty, and I mean this seriously, electricity is no joke, it's dangerous stuff. This video, it's purely for educational purposes. Think of it like seeing the blueprint before the builders arrive. Always, always, always hire a qualified licensed electrician for the actual installation work. They know the local codes and safety rules inside out, and your safety is absolutely non-negotiable. Got it? Okay, good. Let's get into it. First up, let's meet the key players in our solar power team, the components that'll make this all happen. Number 1, solar PV panels. These are our sunshine harvesters, turning sunlight into electricity. Number 2, DC isolators and DC SPDs. Think of these as the safety switches and surge protectors for the DC or direct current side coming from the panels, essential guards. Number 3, DC circuit breakers or DCCB. These guys trip if there's an overload or short circuit on the DC lines, safety first. Number 4, the hybrid inverter. This is the absolute brain of the operation. It converts the solar power into usable AC for your home, intelligently charges the batteries, and seamlessly flips between grid power and battery power when needed. Magic box. Number 5, battery bank, your energy savings account. Stores the sunshine for use at night or during outages. Crucial for backup. Number 6, AC isolator and AC SPD. More safety switches and surge protectors, but this time for the AC, or alternating current side the power your home appliances use. Number 7, AC circuit breakers or ACCB. Protect your AC wiring from overloads, just like the breakers in your main panel. Number 8, ATS or automatic transfer switch. This little hero automatically kicks in during a blackout, switching your essential circuits over to battery power almost instantly. No more fumbling in the dark. Number 9, utility grid connection, where we safely connect to the power company's grid. And finally, number 10, load. That's just a fancy word for your home appliances, the TVs, fridges, lights that actually use the power. Alright, time for some simple math. We want an 8 kilowatt system using powerful 585 watt solar panels. How many panels do we need? First, units match. System size is in kilowatts, panels are in watts. Easy fix. 1 kilowatt equals 1,000 watts. So, 8 kilowatts is 8,000 watts. Next, panel count. Divide the total system wattage by one panel's wattage. 8,000 watts divided by 585 watts per panel is about 13.67 panels. But you can't install 2/3 of a panel. We always round up to make sure we hit or even beat our target. So 14 panels it is. Let's double check. 14 panels times 585 watts equals 8,190 watts, or 8.19 kilowatts. Perfect! Being slightly over our 8 kilowatt goal is actually great. It gives us a little buffer for real-world conditions. Now about wiring those panels up, what we call string sizing. It's kind of like planning how to connect batteries in a flashlight, but, on a much bigger scale. We need to consider the panel specs and our inverter's limits. The key things we look at are, first, panel voltage, especially VOC, which is open circuit voltage. This actually gets higher when it's cold. We absolutely cannot exceed the inverter's max input voltage even on the coldest day imaginable in your area. For our example, we even looked up Jetta's record lows just to be safe. Next, we've got the inverter's voltage range called the MPPT range. This is the sweet spot where the inverter works most efficiently. And finally, panel current, specifically ISC or short circuit current. We need to make sure we don't overload the inverter's inputs. Crunching the numbers with typical specs for 585 watt panels and an 8 kilowatt hybrid inverter, arranging our 14 panels into 2 strings of 7 panels each, so that's 7 panels wired in series per string, works perfectly. Each string connects to its own input on the inverter if it has dual trackers. This setup stays safely within voltage limits even on cold days, operates efficiently in the inverter's sweet spot, and keeps the current well below the inverter's max capacity. Always use your specific panel and inverter datasheet numbers for your project. Safety is paramount on the DC side. For each of our 2 panel strings, we need a DC circuit breaker or DCCB, sized to safely handle the string's current, around 20 amps for our example, and its maximum possible voltage, so we used 400 to 500 volt breakers. Next, a DC surge protector or DC SPD, which shields the inverter from lightning strikes or power surges coming down the wires from the roof. This is usually rated around 500 to 600 volts. And finally, a main DC isolator switch. This is our big off switch for the entire solar array, usually near the inverter, also rated 500 to 600 volts and 20 to 32 amps. Oh, and just a heads up, some inverters actually have this built in. Protecting the battery connection is critical. For a typical 48-volt battery bank paired with an 8-kilowatt inverter, which can push or pull a lot of current, maybe 190 amps or more, we need a hefty battery DC circuit breaker, or DCCB number 2. Sizing this involves first, finding the inverter's max charge or discharge current, always use the bigger number. Next, multiply that by 1.25, which is a standard safety factor for continuous power. Then, choose a breaker rated for that current, like a 250 amp breaker, and make sure the voltage rating is higher than your battery's maximum charge voltage. Think 60 to 80 volts DC. Your inverter manual is the Bible here, so definitely follow its recommendation. And thick cables are a must too. On the AC side, the power your house actually uses, we need to protect the inverter's output and connect safely to your home and the grid. So, first up is the AC MCB for inverter output, which should be sized at 125% of the inverter's max AC output current. For example, 8,000 watts divided by 230 volts is about 35 amps, and then multiply by 1.25 to get around 44 amps. So a 50 amp breaker is the way to go. Next, the AC surge protector, or AC SPD, should be installed near your main panel to protect against grid surges. Look for type 2, 275 or 320 volts and 20 or 40 kiloamps. Then there's the main AC isolator, which is a manual disconnect switch, usually near your utility meter, sized for your home's main service, commonly 63 or 80 amps. And don't forget the MCB for critical loads, which is the breaker feeding the circuits you want backed up by your battery, also likely a 50 amp breaker for our system. Okay, components are sized and ready. Wiring is almost done. But there's one absolutely vital step left before even thinking about turning anything on grounding or earthing. This is your system's safety net, protecting you and your equipment. Here's where it all connects to Earth. First, solar panels and racking. Every single panel frame and the metal rails they sit on must be connected together with a bare copper or green wire, run down to your grounding system. This stops static and provides a safe path for faults. Second, the DC combiner box and inverter chassis, the metal enclosures of these need grounding lugs connected to that same grounding wire. The inverter always has a specific grounding terminal, so use it. Third, the battery bank rack or enclosure, if it's metal, ground it to and connect it to the main grounding wire. Fourth, AC components like the disconnect, ATS, and main panel, all metal enclosures on the AC side must be bonded together and connected to the ground bus bar inside your main electrical panel. And fifth, the earth itself. All these grounding wires must ultimately connect solidly and securely to your main earth electrode or ground rod, buried deep outside your house. This is the final, crucial link that sends any stray electricity safely into the ground. Grounding isn't optional, it's the shield that makes your amazing solar system safe for you and your family. Please, if you're not 100% confident working with high-voltage DC and AC systems, hire a professional electrician. This is not the place to guess. Your safety is everything. Woo! That was a deep dive into planning an 8-kilowatt hybrid solar powerhouse. From calculating panels to sizing breakers and understanding the life-saving importance of grounding, we've covered the essential groundwork. If this video helped demystify solar for you, give us a thumbs up. It really helps the channel. Subscribe and hit the bell for more practical solar and energy independence tips. Got questions or want to share your own solar journey? Drop us a comment below. Stay safe and I'll see you in the next one.